going to look at exercise 11F, and we're going to talk about part 2, which is talking about communication matrices. Okay, so communication matrices are binary, so zeros and ones, and they're square. Okay, and they represent links in communication systems. So it could be social media groups, it could be, friendship groups, or computers. Even computers talking to each other. Can they talk directly or indirectly to each other? Okay. So here's an example of a network diagram. We would have done some of these in exercise 11A. Okay. So you note that some of these communications are only one way. Okay. So you might be able to go from A to D, but it can't go from D to A. But some are two-way. So A to B, A can go to B, and B can go back to A. So we want to represent this in the diagram. So from is always on the column side, and to is always on the row side. Okay. So from A to A, there's 0 links. A to B, there's 1. A to C, there's 1. Yeah, because we can see arrows there. A to D, there's 1. B to A. B to A, yep, there's 1 because there's 1 going backwards. B to B, no. B to C, 1. B to D, 1. C to A. Okay, C does not go back to A. There's no backward arrow, so 0. C to B. C to B, 0. C to C, no. There's no self-communication. C to D. Yes, there's 1, because there's 1 going this way and 1's going that way. D to A. D to A, no, there's no going backwards. D to B, no, there's no link there. D to C, yes. And D to D, obviously, no, there's no self-communication. So this matrix represents the communication between two computers, okay? Whether, it's one way, two ways. A 1 represents there is a direct line communication. A 0 means there's none, okay? This is only one-step communication, so direct line. Okay, I want to draw a communication diagram for this matrix here. Okay, we've got E, W, Y, and K. Okay, let's draw a network diagram. So I'm just going to draw dots to represent the places. So there's only one link at E to, if I'm looking at this row, there's only one link at E to W. Okay, so there's an arrow pointing that way. In this one, W can go to E, so it can go backwards. W can't go to W, can go to Y and K. Okay, so go to Y and then go into a K. Right. For Y, it can only go to W. So Y can only go to W, so it can go backwards. Okay. For K, we can see that there's only one communication, and it's between K and W. So it can go back to W. Okay, so our diagram looks something like that. Okay, so let's look at 1, 2, 3-step communication and redundant links. So in matrix M, there are 1-step communication links, direct links. So I talked about this. We're looking at M. I know that this is direct line only. Okay, so 1-step communication links. Now, if I want to find 2-step communication links, then I need to actually, if I want 2-step communication links, I need to square it, okay? So 2 steps, one step means M only, 2 steps, M squared, 3 steps, M cubed, okay? So it's very important that you understand that if you want the number of 2-step communications, then you may need to square it. Okay, so you need to square it to find the number of 2-step communications there are, and number of 3-step communications there are. What I mean by 1 step is is that in this diagram, E to W is one step, okay? Is one step, okay? To get from E to W, I can get them one step. However, if I want to go to E to K, it's actually two steps, because in the diagram, I need to go through W to get to K. So the actual pathway is E to W to K. So when I look at the matrix m squared and I look at e to k, if I get a 1 there, it means you can either get 1 or 0. If I get a 1 there, it means that there's only one two-step communication between e to k, because I need to go 2 steps to get to k. Okay, so we'll look at this in more detail. So let's calculate what m squared equals to. So it's basically squaring the matrix. Remember from the previous chapter, squaring the matrix means I'm purely squaring the matrix. Okay, so if I square the matrix, I get this value. Okay, so I'm going to screenshot this. So you get a reference as to how I did it. So if I square the matrix, I get this matrix. Let's rearrange this again. So if I square the matrix, I get 1 0 0 0 0 1 0 0 1 1 1 0 1 1 0 0. Okay, so this gives me the number of two-way communication links between two computers. So from and this is A, B, C, D, A, B, C, D. From A to A, there's 1. That's sort of redundant, okay? So in the theory, it says that links are redundant, are not necessarily 0, but they're redundant because we're not interested in A going back to A, okay? We're not interested in A going to something else, okay? So the leading diagonals we can essentially ignore, okay? If they're non-zero, okay? So A to B, A to C. So there's one two-way connection between A to C, okay? So if we look back at our diagram, A to C, there's one two-way connection, okay? So we can go A to D to C, okay? See, we can go from A to C, but it's two steps. That's what I mean by two-way communication, okay? Two-step communication. So this matrix m squared highlights how many two-step communications we can see between two computers. Okay, number of two-step communications. Now, what information's M2 giving us? Which computers have two-step communications? So between we're ignoring the leading diagonals. So between A to C, A to D, B to C, B to D, and C to C we're ignoring. So it's these values, these computers that have that can communicate in a two-way link, okay, in a two-step link. So three-step communication means how many 3 steps can we use to communicate between computers, okay? So indirectly in 3 steps, right? So, and explain what 3-step communication is this. So if I go A, B, C, D, A, B, C, D, you ignore the diagonals, we can see that one 3-step communication exists between A and B, 2 3-step communication exists between A and C, 2 3-step communications between A and D, 1 between B and A, 1 between B and C, 1 between B and D, and 1 between C and D. Okay, so when we're timesing by 3, or not timesing by 3, raising to the power of 3, we're trying to find how many 3-step communications there are between two computers. Okay. So what if the question asks, find a number of 1-2 communications that are possible between two computers? So what this does, when we add m to m squared, the m squared represents the number of two-way communications between computers, and the m represents the number of one-way communication or direct line communication between computers. If I were to use this on a calculator, if I want to calculate this on a calculator, okay, let's just go down a bit, and I'm going to copy. So what I've done here is, I'll do this again. This was my original matrix. I'm going to drag and drop, okay, because I want an m and an m squared. So I'm going to drag and drop here. So I'm going to draw two m's, and you can do this on a calculator to save time. So I'm adding m to m squared. Okay, so I go m squared. You can store it in a calculator, or you can do it like this. Both are fine. Okay, so this is m plus m squared. So I'll just get rid of the keyboard. M plus m squared. I'm going to copy this. So this matrix is m plus m squared, and this tells me how many communication links in total exist between two computers, whether it's direct or indirect. Two steps. So 1 and 2 steps. So the values here tell me. So ignoring the diagonals, the value here is A and A, B, C, D. Between A and D, there are 3, either 1 or 2 communication links, 2-step communication links, which gives me in which A and D can communicate. So it can communicate either directly or indirectly, and there's 3 possible values. So this is what I is actually talking about. So there are 4 paths of no more than 3 steps from A to C. List them. Okay, so let's look at the diagram. So A to C, let's see A to C. A to C is here. So there are 3 paths from A to C. There are, what this matrix is saying